Hello again, APPhysicsC. For this next video, I'm just warning you, I'm a little congested with allergies, so hopefully my speech is clear and intelligible. We're going to talk about integrals today. Um, and there's two different ways I think of integrals. First of all, the integral of a function, f of x, with respect to a variable x, geometrically corresponds to the area underneath the graph of f of x versus x. I'll show you that pictorially in just a moment. Also, what an integral is at its heart is a kind of summation. When you're integrating a function, you're adding something, adding things together. So let's see what we mean by this first kind of definition of an integral. So let's say I have a graph that looks something like this. F of x versus x. And maybe the graph looks like that. So suppose we have two x coordinates, x1 and x2. Well, there's some area underneath the graph. Really, it's the area trapped between the function and the x-axis. And what is that area equal to? Well, that area is equal to, now I'm going to introduce some notation, the integral from x1 to x2 of the function f of x. So this notation here, how you would say this out loud is the integral from x1 to x2 of f of x. Really, you would say with respect to x, with respect to the variable x. And in your math class, if you've seen this sort of thing before, it might be the case that you've identified this little dx here as just a piece of the notation, which tells you, okay, maybe the function f depends on several variables. We're just interested in what a graph of f of x, of f versus the particular variable x looks like, and we want the area under that graph with x on the horizontal axis. It's fine to think about this in that way, but really that dx has some meaning. It's not just notation. It's kind of a necessary part of the expression, as I'll explain in the near future. One thing to note is because the function is positive between x1 and x2, it's strictly positive, I know that this area is going to turn out to be some positive number, some value greater than 0. All right, on the other hand, let's say my x values looked like this. I had, let's say I look between two new x coordinates, x3 and x4. And I'm interested now in this area. Okay, this area is equal to the integral from x3 to x4 of the function f of x with respect to x. We're integrating the function f of x with respect to the variable x. And this area should have a negative value because the value of the function itself is strictly negative in that interval. If you run into a situation where going from, let's say, x1 to x2 spans a region where the function is both positive or negative, then whichever region is bigger in absolute value determines whether the integral itself, the area under the curve itself, is positive or negative. But in this example, I can see right away that the area here is going to be a positive area. The area here is most certainly a negative area. All right, so how exactly does this expression correspond to area? Let's talk about that. I'm going to draw a fresh set of axes, f of x versus x. And suppose my function looks like this, like that, okay? And I have a value, an x coordinate x1 and an x coordinate x2, and I'm interested in finding the area under that graph. I wonder if I can duplicate this for later use. Did that work? No. Did that work? No, there must be a way to duplicate this. Let's see. How about this? No, I'm not sure how to duplicate it. Oh, well, I'll do my best to reproduce it by hand each time. Okay, so I want to find the area under the curve there. So this is my first kind of attempt. The area is approximately equal to, okay, I can't find the area right straight up because I don't understand what this geometric shape is exactly, but I could say the area is approximately equal to, what if I just drew a rectangle that goes from here to here? So I'm just going to draw a rectangle there. Notice the rectangle has a height equal to f of x1, that's this height, and it's got a width equal to delta x, which equals x2 minus x1. So as a really crude approximation to the area, I could say the area is approximately equal to f of x1 times delta x. Now this is a super crude approximation. The value of f of x1 times delta x is the red area over there. And I see I'm missing all of this blue area, which I should also be keeping track of. So not a great approximation. We can do better. We can do better. Perhaps I do something like this instead. The graph of f of x versus x looks something like this. This is x1. This is x2. I see the area that I'm trying to capture. What if instead I break this interval up into 3 subintervals? So the entire range here over which I'm integrating is delta x. So this first tick mark here is a third of delta x over from x1. The coordinate here is x1 plus delta x over 3. The coordinate here is x1 plus 2 delta x over 3. And the coordinate x2 is just equal to x1 plus 3 delta x over 3. That's just because x2 equals x1 plus the full delta x. Okay, so let me draw some rectangles again. The first rectangle will come up to the height of the function at x1 and come over like that. The next rectangle, I'm going to go up until I hit the function, go over and down. And the next rectangle, I'm going to go all the way up till I hit the function, go over, and then come down. It looks like I've got 3 rectangle areas now. They don't perfectly match up with the area under the function. Again, I'm missing the blue area here. I'm missing the blue area here. Happily, I'm actually overestimating when I'm drawing in pink. So the fact that I'm adding on area that I shouldn't be here is partially offsetting the fact that I'm undercounting area under the curve there. And the area of these 3 rectangles is a better approximation to the area under the curve. I think you would agree. The blue minus the overestimated pink is a smaller error than the huge blue region itself is in the first picture. So what does this area equal? It equals f of x1 plus delta x over 3. Sorry, let me back that up. Let's look carefully at the picture here, actually. I'll go very slow. So this first rectangle has a height of f of x1, and it's got a width of delta x over 3. Because the width of the rectangle is just, well, the width of each of these rectangles is just a third of the width of the entire interval delta x. Okay, so the area of the first rectangle is f of x1 times delta x over 3, plus this second rectangle over here has a height equal to the function evaluated at x1 plus delta x over 3. That's the x coordinate where I'm evaluating the function. So the area of the next rectangle is f of x1 plus delta x over 3. And its width is delta x over 3. And the third rectangle, I think you can see, has a height equal to the function evaluated at x1 plus 2 delta x over 3 times delta x over 3 as the width. So there's a common width that each of these rectangles has, which is delta x over 3. And the height of each rectangle is just the value of the function evaluated at different locations. Okay, I'm going to take an eraser to the top picture now. Okay. So we could do even better, as you might expect. Why don't we just use more and more rectangles? Let me give you an idea of what that would look like if we use more and more rectangles. So x1 and x2. Now, look at the rectangles I'm about to draw. What if I drew very small rectangles? Go up to the function, over and down, up to the function, over and down, up to the function, over and down. I think you can see that the gaps between the rectangles and the function itself, the gaps are much smaller now. I bet if you were to add up all these rectangle, well, if you were to see how many rectangles I'm drawing, maybe I'm drawing about 15 or 20 rectangles in total. Some of the rectangle heights, as I am drawing them, are going to start to overshoot. They're going to be higher than the function itself. And the first rectangles I was drawing are smaller in height than the function itself. So I'm kind of leaving out some area here. I'm underestimating the area under the curve there, but I'm overestimating the area under the curve in this right region when I add up the rectangle areas. It's a much better approximation. The area under the curve is approximately equal to, well, I'm kind of summing something up. I'm summing up f of x1 plus I times delta x over n, I'll explain that in a moment, times delta x over n. And I'm doing this sum from I equals, well, 0 to n minus 1. I'll explain all of that. Notice this delta x over n is just 1/nth the width of the entire interval. I'm imagining that I have n rectangles over here. If I have n rectangles, the width of each rectangle is just x2 minus x1, which is delta x over n. In the example below, I had 3 rectangles, so the width of each was delta x over 3. Okay, what's this next piece? What's this next piece all about? Well, the height of each rectangle is the function. First, I evaluate the function at x1. I start with I equals 0, so that this term gets wiped out, and I'm just evaluating the function at x1. But then I have I equals 1 when I jump over to the leftmost vertical side of the second rectangle. And so I end up adding on 1 plus delta x over n. For the next rectangle, I'm adding 2 plus delta x over n. And what this is really doing for me, it's evaluating the height of each rectangle, which is just the height of the function at the leftmost boundary of each rectangle. So that's what I did down here, right? Delta x over 3, then, f of x1, then f of x1 plus 1 delta x over 3, then f of x1 plus 2 delta x over 3. The reason I have n minus 1 up here is the first rectangle corresponds to not adding this term. So the first rectangle has a leftmost edge at x1, and therefore the first rectangle corresponds to I equals 0, and the nth rectangle corresponds to an index I equals n minus 1. Okay, so still we're approximating. We're still approximating. Now here comes the magic. I'm going to say that the area is exactly equal to the limit as n approaches infinity of this sum. F of x sub 1 plus I delta x over n times delta x over n. All right, so as n goes to infinity, I approach having an infinite number of rectangles. The reason that some of these rectangles were underestimating and some were overestimating the true area in any interval of the beneath the function is because the height of the rectangles extend beyond where the function adjusts. The rectangle flatlines for a while on top, even though the function is changing. So in order to fix that, I can make sure that the rectangles are infinitesimally narrow, and therefore they will perfectly tessellate underneath the function itself. So this is what we're looking for. This limit of this rectangle summation process is what we mean by the integral under the function. Instead of using the sigma for a sum, I'm going to use this large-looking S for a sum. It's called an integral sign. The limit of this sum is none other than the integral from x1 to x2 of f of x dx. Now maybe you can see where each part of this expression comes from. We're no longer evaluating the function at a discrete finite number of places, like the left boundary of each rectangle. We're now evaluating the function at every x-coordinate because there's a thin little rectangle that lives at every x-coordinate. Also, delta x over n, remember that represents 1/nth the interval between x1 and x2. As n goes to infinity, delta x over n shrinks down toward 0. Now, taking the limit as n approaches infinity means delta x over n shrinks down toward 0, but it doesn't quite hit 0. It's still got some width. It's just an infinitesimal width, which I'm calling dx. Dx is just what happens to delta x when you subdivide it into infinitesimal sub-intervals. This is each rectangle height. There's a different rectangle at each x-coordinate. This is the rectangle width. There is the same infinitesimal width that each rectangle has. And this thing here I can call dA, which is the rectangle area. dA is an infinitesimal amount of area. You get this infinitesimal area dA by multiplying a height by an infinitesimal width for each of these rectangles, these long vertical rectangles, thin vertical rectangles as you move from left to right. Okay, so how do we actually evaluate integrals? Well, I'll show you how this works in the context of a topic you're familiar with, namely kinematics. So let's say we have a position function that looks like this. X of t, so position as a function of time, equals 5 plus 4t plus 6t squared. Okay, now you should recognize that this is just the position formula for a constant acceleration situation. And I'll write down the general expression for the position formula here. It looks like 5 is the initial position, and 4 is the initial velocity, and 6 is half the acceleration. So the acceleration in the x direction is actually 12 meters per second squared. I'll write down that information here so we remember it. X initial is 5 meters. The initial velocity in the x direction is 4 meters per second. And the acceleration is constant in the x direction. That's why this function has the same form as our constant acceleration kinematics formula. The acceleration is 12 meters per second squared. Okay. The x component of the velocity as a function of time. I know what the generic formula looks like. V final x equals V initial x plus acceleration in the x direction times time. So I can actually write that down. And the initial velocity in the x direction is, as we mentioned, 4 meters per second. The acceleration in the x direction, as we mentioned before, is 12 meters per second squared, which then gets multiplied by time. So I know what, given the position formula, position is a function of time, I can immediately write down the velocity formula. Now, what's the relationship between these two things? Velocity is the rate at which position changes. Velocity is the derivative of position with respect to time. In fact, you can apply the power rule that we learned in the previous video to obtain this velocity formula. Bring down the 2 and multiply, you get 12, and you demote the power to 1. Bring down the hidden 1 and multiply, you get a 4 out front, and you demote the power to 0. 4t to the 0 is 4. This is like 5t to the 0. If you bring down the 0 and multiply, it gets wiped out. There is no term down here corresponding to that constant term. So I can take the derivative of the position function with respect to time to get the velocity function. Perhaps there's some process that would take us the other way, that would take us from the velocity function to the position function. Indeed, there is, and this process is none other than integration. Integrating the velocity function with respect to time will get us the position function. Right away, you should appreciate that there is an intimate relationship between derivatives, which have to do with slopes, and integrals, which have to do with areas. And the foundations of calculus deal in no small part with this relationship. Well, what if I were to ask you what's the displacement between 1 second and 3 seconds? I want to know the displacement of the object between 1 second and 3 seconds. Well, I know what that is. The displacement between 1 second and 3 seconds is just the position final, which is the position at 3 seconds, minus the position initial, which is the position at 1 second. So to find the displacement, I simply plug in 3 seconds. I'll leave out units here, but I plug 3 seconds into the position formula. Okay, I'll bracket that. And then I subtract, and I plug 1 second into the position formula. All right. So this is the displacement between 1 second and 3 seconds. This is going to seem strange. I'm not going to simplify this all the way. But I am going to note that I have a 5 in the first set of brackets, and then I subtract a 5 in the second set of brackets. So that constant term of 5 goes away, and I end up with 4 times 3 plus 6 times 3 squared. I'm going to bracket that, minus 4 times 1 plus 6 times 1 squared. I'm going to bracket that. And now I'm going to come up with a notation for this. All right, I'm going to invent some notation that tells me to do this. Where I'm plugging in the 3s and the 1s, those are actually time values. So what this is 4t plus 6t squared evaluated from 1 to 3, from 1 seconds to 3 seconds. What does this mean over here? It means plug in the top number, you get this, then subtract and plug in the bottom number, you get this. All right? It's just notation. I'll give you an example. Suppose I have 5t evaluated from 2 to 3. First, I plug in the top number, then I subtract and I plug in the bottom number. And this is 15 minus 10 equals 5. So 5t evaluated from 2 to 3 equals the number 5. And 4t plus 6t squared evaluated from 1 to 3 equals this previously written line, which equals this previously written line, which equals x of 3 minus x of 1, which is what we're looking for, the displacement. Okay, now at this point, you should start to think about the following. This is all true, Mr. Frankel, but what the heck does this have to do with integrals? Well, I'll explain. Trying to adjust my color here. Okay, I'll explain. If velocity is constant, then displacement is just velocity times time. If velocity is constant, if there's no acceleration, the displacement of an object over a time interval is just the constant velocity during that time interval times time. If the time interval is super, super tiny, you'll get a super, super tiny displacement. I'm going to write that tiny displacement as dx. It's an infinitesimal displacement. An infinitesimal displacement is just equal to the velocity of the object times an infinitesimal time interval. So if only a tiny, tiny amount of time goes by and I'm moving at some velocity at that time, only a tiny, tiny displacement is achieved. But this is always true because a tiny, tiny time interval, an infinitesimal time interval dt, is one in which there's no time for the velocity to change. The velocity has one distinct value at each infinitesimal moment of time. Now, the entire displacement during a time interval, say t1 to t2, the entire displacement during a time interval should just be the sum of all the tiny displacements that occur at each moment during that time interval. That is, the displacement between t1 and t2 should just equal the integral of all the tiny displacements, which I can write as the velocity integrated with respect to time from t1 to t2. Let's take a moment to appreciate this. So multiplying the velocity at a particular time by the tiny time around that moment gives me a little displacement dx. The integral adds up all of those little displacements, giving me the overall displacement. So the integral of velocity with respect to time from time 1 to time 2 is not quite the position, but it is the change in position. It's the displacement between time 1 and time 2. But the displacement between time 1 and time 2, let's say time 1 is 1 second and time 2 is 3 seconds, is just this. Therefore, we have to figure out how to go from the velocity function that we're integrating to this expression, which resembles the position function in some way. All right, let's walk through that. I really wish I could move these things around easier. There must be a way. What if I highlight this whole thing and slide all this over here? Okay, good enough. Okay, so the displacement between 1 second and 3 seconds should be the integral of the velocity function, which I'll remind you is a function of time with respect to time from 1 second to 3 seconds. This is the integral from 1 second to 3 seconds of, well, the velocity function is 4 plus 12t. So I'm multiplying the velocity at each time between 1 and 3 seconds by a little bit of time. And that is giving me little displacements that occur at each of the infinite moments that exist between 1 and 3 seconds. Now, I know what this should turn out to be, okay? This should turn out to be the expression for the displacement that we already obtained, namely 4t plus 6t squared evaluated from 1 to 3. So if someone asks me to integrate this function, I need to figure out how to end up with the correct answer. You end up with the correct answer by applying some rule to this polynomial function. And we said at the beginning of this slide that taking the derivative of velocity with respect to time, taking the derivative of position with respect to time gets you velocity. And now we see that integrating velocity with respect to time gives you the change in position. So whatever rule brings us from position to velocity, some opposite rule is close to what we want to go from velocity to position. The power rule, where you bring down the exponent and you demote the exponent, is how we take the derivative of position to get velocity. We have to apply some inverse power rule, I guess, to go the other way. So how do I start with this and end up with that? Well, the first thing to note is that this 4 can be thought of as 4t to the 0. And this 12t is like 12t to the first. So this is what we're going to do. 4t to the 0, promote the 0 to a 1, and divide by the new power, 1. Plus 12t to the first, let's promote the 1 to a 2, so I'll have 12t squared, and divide by the new power of 2. This gives us 4t plus 6t squared. And that is what we want to evaluate from 1 to 3 in order to get the displacement. So apparently the way you integrate a polynomial function is you apply the reverse power rule. The first thing you do is promote the exponent by 1. You add 1 to the exponent. Then you divide by the new exponent. You have to do it in this order. You have to first boost up the exponent of the variable by 1 and then divide by the new exponent. So we end up with 4t plus 6t squared. We evaluate it from 1 to 3, and that will get us the displacement that we're after. All right, let's look at another concrete example. Suppose I have the following function. Suppose I have f of x equals, let's see, 9x squared plus 3. All right, what does this function even look like? It looks like a parabola that is smiling and hits the vertical axis at 3. Let's say I want to integrate that function with respect to x from x equals 1 to x equals 2. So maybe this is x equals 1 and this is x equals 2. Geometrically, the integral of this function from x equals 1 to x equals 2 is this red shaded region. What is the area of that red shaded region? Well, the area of that red shaded region is the integral from 1 to 2 of the function 9x squared plus 3 with respect to x. And now I can apply the reverse power rule. This is 9x squared. I should promote the power to x cubed and divide the coefficient by the new power. 9 divided by the new power of 3 is 3, plus this 3 is really 3t to the 0. So I should promote t to the 0 to t to the first power, which is just t itself, and divide the coefficient by the new power. The new power is 1, so 3 divided by 1 is 3. And then I evaluate this from x equals, I'm mixing up my t's and my x's. Sorry, x is the independent variable here. I should stick to it. X is the independent variable. X is the independent variable. Okay. So I'm evaluating now this expression from 1 to 2. It means I first plug in a 2, which is the top value. Then I subtract, and I plug in the 1. Okay, so I just plugged in a 2 into this expression. That's what you see here. Then I plugged a 1 into the same expression. You see it there, and I subtract. Let's simplify. 3 times 2 cubed. 2 cubed is 8. 3 times 8 is 24 plus 6 minus 3 plus 3. And this just equals 24. So I guess the area underneath the parabola 9x squared plus 3 is equal to 24. It's getting a little late in the day. Hopefully I didn't make any arithmetic error over here. That would be bad considering I am trying to teach you this for the first time. Don't forget, though, what this actually boils down to. It actually boils down to the following. Whoops. Between x equals 1 and x equals 2, we are drawing an infinite number of infinitesimally wide rectangles. Each rectangle has a height equal to the function, 9x squared plus 3, and a width equal to dx. And we're integrating. We're adding up the areas of all those rectangles in order to get the true perfect area under the curve. Okay, I'll show my face again just before I end the video. So we apply the power rule in order to find the derivative of a function with respect to a variable, and we apply the reverse power rule to find the integral of a function with respect to a variable. The power rule and the reverse power rule only work if you have polynomial functions. So we'll stick to polynomial functions to start. Okay, the last thing I want to show you is the relationship. The relationship between derivatives and integrals. The power rule and the inverse power rule are just inverse algorithms you apply to polynomial functions to integrate them, that is to find the area underneath them, or to find their slope values, to find their derivatives. The relationship between derivatives and integrals is sometimes called the fundamental theorem of calculus. I'm going to give you a very informal idea of what that involves. So we saw that the displacement of an object is equal to the integral from some initial time to some final time of the velocity of the object, integrating with respect to time. Oh, let me get the lights. Okay, but the function we're integrating here, right? The velocity function is just the derivative of the position function. So when we integrate the derivative of a function, we get back a change in the function itself. Integrating the derivative of a function gives us a change in the function itself. I'm going to write that down very generically. The integral from t initial to t final of, I'll call it df dt with respect to t, is equal to f evaluated at t final minus f evaluated at t initial. So I integrate the derivative of the function f with respect to time with respect to time. I'm integrating the derivative of the function with respect to time, and I'm integrating with respect to time. I get back the change in the original function f between the two times. Can we make sense of this? Well, I can rewrite this over here. df is a little change in the function, up and down. dt is a little change in time, to the right. When I multiply that by a little change in time, you could almost imagine these dt's kind of canceling out. If you imagine it like that, then you're imagining that you're adding up, you're integrating, you're adding up from t initial to t final, all the little df's. But all the little df's are all the little changes in f. What if I add up all the little changes in f's between t initial and t final? Then I get delta f, the overall change in f between t initial and t final, which is just the function evaluated at t final minus the function evaluated at t initial. This works because multiplying a slope by, I'm going back to the language of, when you first started studying slopes in math. If I multiply a slope by a change in x, I get a change in y. All right. Multiply a slope by a change in x, and I get a change in y, because the slope is none other than change in y over change in x. So what are the analogies over here? Okay. The function f is like y. The independent variable x is, I'll say it's like x, but it is x. The derivative of y with respect to x is like the slope. In fact, I'm putting like in quotes again. It really is an unnecessary word there. It is the slope. When I multiply the slope of a function by a little change in the independent variable, that's on the horizontal axis, I get a change in the vertically plotted variable, a change in the function itself. And when I integrate, all I'm doing is I'm adding up slope times change in x, or change in t, if you will, plus slope times change in x, plus slope times change in x. Adding up the slope of a function times the change in x is giving me all the little changes in the function itself. If I integrate, I get the overall change in the function itself. So slopes and areas, it turns out, have this intimate relationship. Okay, I'll post this and have a good evening, morning, or afternoon whenever you're watching this video. Bye for now.